Good morning to everybody. My name is Pablo Merino. I'm working at the Universidad Politécnica de Madrid, and together with Professors Fabricio Macià and Antonio Souto Iglesias, I have developed this work, which title is On the Convergence of the Solution to the Continuous SPH Heat Equation. The contents of my presentation are the following. First, I will talk about motivation. Then I will introduce the problem and the setting. After that, I will present the Fourier representation of the SPH Laplacian operators, which will allow me to briefly sketch the convergence of the SPH heat equation. After that, I will talk about the regime when the interparticle distance is of the order of the smoothing length by presenting a numerical example. And I will close this presentation with conclusions and future work. Regarding motivation, well, convergence is a very relevant topic in any numerical method, so it is in SPH. And there are certainly very interesting works covering this topic, mainly that by Franz and collaborators or the work by Ben Musa and Villa, but there are very few studies focused on diffusive operators. Regarding this specific topic, I want to highlight the work by Violot and collaborators, in which the spectral properties of the discrete Laplacian, when periodic boundary conditions are involved, were studied. Despite all that, there is no proof of convergence of any SPH equation when diffusive operators are involved. The aim of this work is to contribute to the important goal of deepening into the convergence of the SPH method by presenting the first mathematical proof of convergence of an SPH equation involving diffusive operators. Okay, let's start from the beginning. First, and in order to set ideas, it is important to keep in mind that the theoretical developments presented in the following concern the regime in which the interparticle distance is much smaller than the smoothing length. The SPH kernel is defined as usual by scaling a function w, which is considered to possess certain properties, the most important of them for us being its radial symmetry. This is a feature that I will be using very often throughout this work. Another important character in this story is the derivative of the kernel, which is often expressed using the function f, defined as follows, and which plays a major role in all this development. Already, the function f allows to write the SPH Laplacian operators in a very simple way. Let me show you. Here you have the Morris Laplacian operator on top and the Monaghan Cleary-Gingold's approximation below. Note that the Morris Laplacian is applied to a scalar field, while the Monaghan Laplacian is applied to a vector field. These two expressions are relatively simple and are both of them written in terms of the function f. We also have this function omega here, defined as follows, and representing the matrix of the orthogonal projection. Both Laplacian operators can be derived from the SPH approximation to the Hessian matrix given by Español and Revenga, and which formula is the following. One of the goals of this work is to give an explicit expression to the Fourier representation of this approximation to the Hessian matrix. Consider also the following heat equation with no boundary conditions and in which an initial condition has been set. I will now play the classic game with the Fourier transformations. So, applying Fourier transforms to both sides of the equation, I can translate this problem, a partial differential equation, into this other, which is in the form of an ordinary differential equation, much simpler to solve, and whose exact solution is the following. And now, applying inverse Fourier transform, I can get back to the function u. Note here this minus chi square, which is the symbol of the Laplacian operator. The symbol of the operator is simply its Fourier representation. It's important to keep this in mind because in the following I will be comparing the symbol of the exact Laplacian operator to those of the SPH versions. Okay, now consider the SPH version of the heat equation in which the exact Laplacian operator has been replaced by an SPH1. The exact solution is already known and is given by this expression, and here we have introduced the symbol of the SPH Laplacian operator. The goal from now on would be to give an explicit expression to this function phi. So, for the sake of simplicity and as an example, let me present now the case of the Morris Laplacian. This expression is an alternative representation of the Morris operator, where I use this function fh instead of the function f itself, and fh here is defined in a similar fashion to that used with the kernel. So let me introduce the function g, which is simply an extension of the function f to the whole space. Remember that f is a radial profile, so it's only defined for positive real numbers. Introducing the function g in the expression above, I can get the following equivalent equation, and after applying Fourier transforms to this equation, I finally get the equivalent Fourier equation. Note that this convolution has been transformed into a product, and this integral here is simply lead us to the evaluation of the function gh hat at 0. Now, we only need to consider the relationship between gh and g, given by the following expression, and now the only problem left is to compute the Fourier transform of the function g. Let's go for it. So, first, consider the nature of the function g, that has been defined as an extension of the function f, and also take into account the link between the gradient of the kernel and the radial profile of its derivative. With all this in mind, we arrive to the expression that you see here, and rearranging the terms, we get the following equation. Applying Fourier transforms now to both sides, we get the corresponding equation in the Fourier space. Now we use that the Laplacian operator is the same as the divergence of the gradient, and we get the simplified version of the previous equation. At this point, I will use that both the kernel and the function g are radial functions. This implies in particular that their Fourier transforms are also radial functions, and then allows me to introduce the radial profile of the Fourier transforms of the functions g and w. Now, introducing this in the previous equation and taking into account how this works with the gradient, we finally arrive to the following ordinary differential equation. This is a very easy equation that we can solve to get an explicit expression for the function f in terms of the radial profile of the Fourier transform of the kernel. Now, by applying a change of variable in the integral above and just introducing the function phi, we get finally an expression for the symbol of the Morris Laplacian operator. In the case of the Monaghan Laplacian, we have to consider two different cases. First, the case in which U is a divergence-free vector field. In that case, the Monaghan Laplacian symbol is given by this expression, where this new function phi is defined as follows in terms of the previous function phi, computed for the case of the Morris Laplacian, and the function psi, given by the expression below. In the case when the Monaghan Laplacian is not applied to a divergence-free vector field, actually, the Monaghan Laplacian operator does not approximate the exact Laplacian itself, but rather the following operator. Applying Fourier transforms, here we get the symbol of the exact operator, and following a similar procedure to that presented for the Morris Laplacian, but a bit more complicated and technical, we finally get the expression for the symbol of the Monaghan Laplacian. In a similar way, we can also get an explicit expression for the symbol of the Español and Revenga's approximation to the Hessian matrix. At this point, let me point out that both expressions, that of the Monaghan Laplacian and that of the approximation to the Hessian matrix, can be obtained only by knowing the functions phi and psi, which can be obtained from the radial profile of the Fourier transform of the kernel. Let me show you now the symbols of the Morris Laplacian on the left and the Monaghan Laplacian for a divergence-free vector field on the right, computed for different kernels and compared to the symbol of the exact Laplacian in dashed lines. Note that for all the kernels considered, the symbols converge to the symbol of the exact Laplacian when h is made small. For a fixed value of h, however, there are kernels for which the approximation is more accurate, notably the Wendland kernel C6. So, with the previous results, and taking into account the properties of the SPH Laplacian symbols, well, more precisely the properties of the function phi and psi, we can establish the convergence of equations involving diffusive operators. In particular, the heat equation is a canonical example, so let us define the error between the exact solution and the SPH solution, and this leads us to the following expression with which we can bound the error by this term here on the right. This, in particular, allows us to establish the convergence in terms of the L2 norm. Now, let me talk about the regime in which the interparticle distance is of the order of the smoothing length. The heat equation is solved in one dimension using Eulerian SPH, and a Gaussian function is used as an initial condition. The convergence is studied when h tends to 0 by keeping the interparticle distance over smoothing length ratio constant. This is an interesting choice because it represents the common practice in SPH, while it's important to remark that under this regime, we are not approaching the problem presented before, that is, the integral problem at the continuous level. You can see in the figure on the right that the errors do not converge to 0 but to some limiting value instead. This is not good news, while this behavior is not entirely surprising for us, as this pattern was already found when studying the convergence of the hydrostatic problem. Anyway, the exact mechanism under this behavior has not been fully understood yet and is left for future work. Conclusions and future work. The Fourier representations of the two most common Laplacian operators in SPH, Morris and Monaghan Cleary-Gingold's, and also of the Español and Revenga's approximation to the Hessian matrix have been presented. As a consequence, the convergence of the integral SPH heat equation is established. The numerical experiments that have been carried out suggest that there may be convergence problems originated at the discrete level and which exact mechanism has not been fully understood yet. As a future work, the problems originated at the discrete level will be studied using analytical tools. Also, the approach followed here for the heat equation will be applied to more complex equations, notably the advection-diffusion equation or the Burgers equation. Thank you very much for your attention.